Welcome to the next lecture. In previous lecture we have seen per unit analysis of three-phase system and per unit analysis of three-phase transformer. In this lecture we will see per unit system with changes in base quantities. The first question here is, what is the need for changing the base quantities? Sir, in practice our power system not having a single element. If you have a single element, there is no need of changing the base quantities. But actually our power system is an interconnected system. It is an interconnection of n number of elements. For example, if we take a simple system where we have a generator cascaded with a transformer and that is cascaded with transmission lines. That means how many elements? We have three elements. Okay. So we have a generator, then transformer, then transmission line. If you really notice, the per unit impedance of the generator is given, the per unit impedance of the transformer is given, per unit impedance of the transmission line also given. But these values are given by the manufacturer by considering the equipment rating as default base. That means, for example, let's say it is 11 kV generator with 100 MVA rating, and its per unit impedance is given on the nameplate details as 0.2 per unit. Sir, how the manufacturer of the generator is calculated? The per unit impedance is 0.2 per unit by dividing actual impedance by base impedance. Okay, but what is the base? The base is calculated by considering machine rating as default base. That means, what is the jet base here? Line voltage base square by upper end power base. That means VLB square by S base. What is VLB? 11 kV. What is S base? 100 MVA. That means by considering the machine rating as base, the manufacturer is calculated the per unit impedance. Okay, that's about the generator story. Next we have a transformer, right? Let's say this is a 11 kV by 132 kV transformer, and its rating is, let's say, 120 MVA, and its per unit impedance on the nameplate details is marked as 0.1 per unit. Okay, the transformer manufacturer has given me the per unit impedance is what? 0.1 per unit. Now again the question is, how the manufacturer of the transformer is calculated this per unit impedance? For example, on the primary side, how he has calculated? Because we know primary side per unit impedance, secondary side, that means the impedance referred to primary of a transformer in per unit form, impedance referred to secondary of a transformer in per unit form are always same. So that's why, so I am taking an example of primary side. So in primary side, what is the base value the transformer manufacturer has considered for calculation of per unit impedance? He has considered 11 kV is the base voltage and 120 MVA is the base MVA. But for a generator, 11 kV is the base voltage and 100 MVA is what? Base MVA. That means the generator base and transformer base are same now? No, they are not same. Here 100 MVA base, here 120 MVA base. Similarly, for example, let's say there is a transmission line. Yes, it is a 132 kV line and its rating is maybe 150 MVA. Okay, clear? Its per unit impedance is given me as 0.2 per unit. So what you can understand from here is, sir, the transmission line per unit impedance is calculated on what base? Line voltage base is 132 kV and MVA base is what? 150. Okay, that means this is what an interconnected system where we have a different elements and every element is given with its per unit impedance by considering its own rating as base. Clear? So that's why when you are dealing the analysis of this kind of an interconnected system, first you must convert the per unit impedances of all the elements to a common base. After calculating the per unit impedances of all the elements onto a common base, next we draw the impedance diagram, then we can do the respective analysis. That means maybe fault analysis, maybe stability analysis, maybe load flow analysis. But before doing all these analysis, you must convert the impedances of all the elements onto a common base. So once you are converting impedances of all the elements onto a common base, there is a need for changing of base quantities. Clear? Now we will see a simple example by which we can understand how to calculate the new per unit impedance based on new base quantities. Okay. For understanding this, I am just considering a generator. Generator KVB old. KVB old. By default, KVB means I told you line voltage base. KVB old is I know, okay, and MVAB old also I know. That means on KVB old and MVAB old, Z per unit is calculated. I can say Z per unit old is already calculated. Okay, so this is the Z per unit old of this generator is calculated on what? KVB old and MVAB old. Now the question is, what is Z per unit new? What is Z per unit new? On what base? On new voltage base. KVB new and what? MVAB new. On the new voltage base and new MVA base, I need to calculate what is the Z per unit. Clear? To solve this, we need to take one simple fundamental, that is, per unit value may not be unique, but actual values are always unique. Actual impedance of the generator will not change, but per unit impedance of the generator will change based on the base value what you are selected. Using that simple principle, I am going to calculate the Z per unit new. Okay, let's see. What is Z per unit old? Already given to me. KVB old is given and MVAB old is given. Shall I calculate Z actual from here? Okay, what is Z actual? Shall I write Z actual new, Z actual old? No need to write, because actual impedance is always same. Even if you are changing the base quantities, actual impedance will not change. So that's why Z actual equal to what? Z per unit old I already know, and multiplied with what? Z base old. Okay, clear? Z per unit into Z base is the Z actual. Tell me, what is Z base old here? Z per unit old multiplied with, what is Z base old? Z base old is nothing but what? KVB old square divide with what? MVAB old. KVB old divide with what? MVAB old. That is the Z base old. Clear? Now this is the Z actual. If I divide the Z actual with what? Z base new, I will get the Z per unit new. Okay, so Z per unit new is equal to what? Z actual by what? Z base new. Okay, clear? But what is Z base new? KVB new whole square by MVAB new. So that's what I am going to substitute here. But what is the Z actual? Z per unit old, Z per unit old multiplied with KVB old whole square divided with MVAB old. Clear? This is what? Z actual. Now divide with Z base new. What is Z base new? The whole function you need to divide with Z base new. Z base new is nothing but what? KVB new whole square divide with what? MVAB new. Clear? Now I am going to rewrite this in a simple form. Z per unit new equal to Z per unit old multiplied with KVB old square by KVB new square. Okay, that means simply KVB old divided with KVB new whole square. Clear? Multiplied with this MVAB new. When you take this side, it will be coming in the numerator and denominator is MVAB old. So MVAB new divide with MVAB old. So this is the simple formula to convert the old per unit impedance to new per unit impedance. And this formula is very, very important, sir. By using this formula, we are going to convert a complete interconnected network onto a common base. That means we are going to calculate the per unit impedance of every element in an interconnected system onto a common base. Now we will solve this example. The per unit impedance of a 3-phase 11 kV 100 MVA generator is 0.1 per unit. Calculate its per unit impedance on 200 MVA 22 kV base. Clear? So in this question, what is KVB old? KVB old is what? 11. What about MVAB old? MVAB old is 100. What is Z per unit old? Is 0.1 per unit. Simply 0.1. Okay. Now, what is KVB new? 22. What is MVAB new? That is 200. Now we need to calculate what is Z per unit new. What is the Z per unit new formula? Z per unit new equal to Z per unit old multiplied with KVB old by KVB new whole square multiplied with MVAB new divided with MVAB old. So let's substitute, sir. Z per unit old is how much? 0.1. KVB old is 11. KVB new is 22. And MVAB new 200. MVAB old is 100. So if I solve this, we get 0.05 per unit. That is the new per unit impedance. Now we will solve this example. A single line diagram is shown below. Considering generator rating as base, calculate the new per unit impedances of all the elements. Is clearly mentioned. What is the base you need to consider? Generator rating as base. You need to calculate the new per unit impedances of what? All the elements. Okay, clear. So, but when you are solving an interconnected system, you should be very careful with the transformers. Okay, sir, simple fundamental rule is MVA rating in the primary and MVA rating in the secondary of a transformer is always same. Correct or not? So that's why for a complete system, what is the new base MVA? Again I am saying MVA rating of the transformer in the primary, MVA rating in the secondary of a transformer is same. Okay, transformer MVA primary side is 50, secondary side also 50. Indirectly speaking, this is the old base. Now what is the new base? He is clearly mentioned. Consider the generator rating as base. Okay, generator rating as base. That means what is the MVAB new? MVAB new is what? 100. For what? Generator. For transformer primary also MVAB new. I am not talking about MVAB old. MVAB old is 50. He has mentioned MVA rating as base. Tell me, what is the MVAB new for transformer primary? 100 only. But transformer secondary? 100 only. Why? MVA in the primary and secondary are always same. Now, what is the MVAB new for transmission line? 100. MVAB old also what? 100. Okay, clear. So that means for a complete network, MVA base is what now? New MVA base is what now? 100. Okay, clear. So because of the presence of transformer, the MVA rating or MVA base will not change, but voltage base will change. Clear? How the voltage base will change, we will see now. But before that, what is the MVA base for complete system? For a complete system, the MVAB new equal to what? 100. Okay, complete system means for this generator, for this transformer, for this transmission line, the new MVA base is 100. But what about new voltage base? Now, at every transformer you have to pay attention here. Let's see here. The transformer primary and this side is what? Transformer secondary. Now till here, what is the KVB new? KVB new is 11. Why? Is clearly mentioned, consider the generator rating as base. That means till the transformer primary, till this transformer primary, KVB new is 11. What about the KVB new in the transformer secondary? What is the KVB new in the transformer secondary? For that, you must shift 11 kV to high voltage side using line to line transformation ratio. So indirectly speaking, for this transformer I am given 11 kV in the primary. 11 kV in the primary I given. Okay, what is the secondary voltage I get? Clear? For understanding this, check the transformer ratio. What the transformer is saying, you give me line voltage 11 kV, I will produce the secondary voltage as what? 120 kV. What this transformer is saying, you give me primary line voltage 11 kV, I will produce secondary line voltage as what? 120 kV. Okay, clear? So using that simple principle, we can calculate what is the secondary line voltage. Okay, now tell me, kVB new in the low voltage is 11 kV. What is the kVB new in the high voltage? So that is kVB new in the high voltage side is equal to what? kVB new in the low voltage is 11. Now transformation ratio, line to line transformation ratio you have to use, because we need a line voltage. I given a line voltage, we need a line voltage, that's fine. Okay, 11 I given. Okay, but what this transformer is saying, I will shift 11 to 120. So that's why 120 by 11 you have to write here. So what I get now? 120 kV. Clear? So that means kVB new for generator and transformer primary is 11. kVB new for transformer secondary and transmission line is 120. Now we can calculate what is the Z per unit new for every element. Okay, but is the Z per unit new of a generator will change? It is not going to change. Why? What is the kVB old for generator? 11. MVAB old for generator? 100. But in the problem what is mentioned? Consider the generator rating as base. Considering generator rating as base. Okay, so that means what is the new kVB in generator circuit? 11. What is the new MVA in generator circuit? Is 100. Okay, new value, old value is same. That's why Z per unit new equal to Z per unit old. Okay, so I will write a formula first here. Z per unit new equal to Z per unit old multiplied with kVB old by kVB new whole square and multiply with MVAB new by MVAB old. Clear? So this is how we can calculate Z per unit new. Right, sir? Now coming to the first element, generator. Generator. So generator, what is the kVB old? 11. kVB new also 11. Clear is mentioned, generator rating as base. So 11 kV is the kVB new, kVB old also 11. MVAB new 100, MVAB old also 100. Okay, MVAB new, MVAB old are 100, kVB new 11, kVB old also 11. So that's why Z per unit new and Z per unit old are what? Same for generator. So directly I am writing what is Z per unit new for generator, which is 0.1. After that, transformer, sir. Sir, when you are dealing with the transformer, the per unit impedance, if you evaluate from the primary side or if you evaluate from the secondary side, both are same. That's why it is up to you. You can take primary side or what? Secondary side. We can get the same value. Anyway, what is the primary side kVB old? 11. What is the primary side kVB new? 11. Okay, I will write here Z per unit for a transformer new equal to Z per unit old. What is Z per unit old? 0.2. Okay, multiplied with what is kVB old? kVB old 11. kVB new also 11 in the primary side. Then multiplied with MVAB new by MVAB old. What is MVAB new? For complete system, new MVAB is what? Generator MVA. What is that? 100. So MVAB new is 100. What about MVAB old? MVAB old is what? 50. So what I get now? 11, 1 square, 100 by 52, 2 into 0.2, which is what? 0.4 per unit. That's what Z per unit new for a transformer. Now coming to transmission line. Now, for a transmission line, what is a Z per unit new? We need to calculate. Okay, so how to calculate that? Z per unit old is 0.2. I'll write here Z per unit new equal to Z per unit old 0.2. What is KVB old? Because KVB old by KVB new whole square, na? What is KVB old? KVB old is what? Transmission line rating 132 by KVB new in a transmission line circuit. What is the KVB new? 120. Okay, 132 by 120. Don't take 11, sir, that is blunder, and divide with MVAB new 100, MVAB old also 100. So I can write 100 by 100. Now if I solve this, we get 0.242 per unit. So that is how we need to calculate. Okay, so we are calculated the per unit impedance of a generator is 0.1. New per unit impedance of a generator is 0.1. New per unit impedance of a transformer is 0.4, and new per unit impedance of a transmission line is 0.242 per unit. Now we will go through this example. In this question it is given that a single line diagram is shown below. Considering generator rating as base, calculate the new per unit impedances of all the elements. Okay, here we have a total 5 elements. We have a generator, transformer 1, transmission line, transformer 2 and motor. This is how they are interconnected. It's a 11 kV generator which is interconnected with 10 kV by 100 kV. Generally you may get a doubt here, how a generator of 11 kV interconnected with 10 by 100 kV. Practically this is not correct. Practically it might be 11 kV by 100 kV. But just to introduce the complexity, a numerical question may be framed like this. But don't think that practically this is what the situation. Practically, suppose if it is a generator is 11 kV na, then primary voltage rating is 11 kV. No need to worry about that. Okay, clear? Since it is a problem, just treat it as a problem, but don't think that it is the circuit which is really appearing in the power system practically. No, that's not correct. Okay, clear? Now coming to the point, let's take the generator rating as base. Okay, so what is the MVAB new? Generator MVA. What is generator MVA? 100 MVA. That means for a complete system, what is MVAB new? 100 only. That means generator MVAB new is 100. Transformer 1 MVAB new is 100. Transmission line MVAB new is 100. Transformer 2 MVAB new is 100, and this motor also MVAB new is 100. Okay, clear? Because MVA is not going to change to primary to what? Secondary of a transformer. MVA will not change from primary to what? Secondary of a transformer. Okay, that's why for a complete network MVAB new is what? 100. But the voltage base will change. Where the voltage base will change? From primary to what? Secondary of a transformer. The voltage base will change. Okay, let's see how it is changing. So at every transformer you have to put a focus here. So there is a transformer here and there is a transformer here. In between these two transformers we have a transmission line. Now let's see, sir. There is a section 1, there is a section 2 and what? Section 3. Since we have two transformers here, that's why we got 3 sections. Now have a look, sir. In this section 1, what is the KVB new? 11 only, because he is clearly mentioned take the generator rating as base. What is the generator rating? 11 kV. That is a new base for us. Okay, so that's why. So in this circuit KVB new is what? 11. Clear? But what about the KVB new in the next circuit? That means from the high voltage side of the transformer to high voltage side of this transformer. From this point to what? This point. That means this and this will be included in that. Okay, what is the KVB new in this section? So use the transformation ratio and you shift from what? Primary to secondary. Okay, you shift the voltage from primary to what? Secondary. Indirectly speaking, it is a 10 kV by 100 kV transformer. I given what? 11 kV as a primary line voltage. What is the secondary line voltage? I am asking. What you given? 11. Correct or not? I given 11 kV. That's what the KV be new here. No? That's why I given, indirectly speaking, I given here 11 kV. You just think like that. I given here 11 kV. What is the line voltage I get on the other side? So for that you need to use line to line transformation ratio. If I give 10, I will get 100. If I give 11, how much I will get? For that 100 by 10 is the line to line transformation ratio. Because I am interested about only line voltages. Okay, now 11 kV is the line voltage in the primary. What about the line voltage in the secondary? So what I get now? 110 kV. Okay, till what? Till here. Till here the line voltage new is what? 110 kV. That means KVB new. KVB is by default line voltage. Line voltage base new till this point is what? 110 kV. Now after this we have again a transformer. Because of the transformer, the KVB new will change from what? High voltage to low voltage. Otherwise low voltage to high voltage. But here what? 120 kV is the high voltage. 120 kV side, what is the KVB new? 110 kV. And 20 kV side, what is the KVB new? I need to calculate. For that, again, KVB new on this circuit will be what now? KVB old on this circuit is 110. And you need to use what? Transformation ratio of transformer, 20 by 120. 20 by 120. 20 by 120 means what? This is 6. That means 110 by 6. 110 by 6 kV. Okay. No need to write kV. We are already written here KVB new. Okay. Anyway, so 110 by 6 is the KVB new in this circuit. Clear? Now tell me, for a complete system, what is the MVAB new? MVAB new for complete system. MVAB new for a complete system is 100 only. Because he is clearly mentioned, take the generator rating as base. That is what? 100. Now we need to deal with individual element to calculate what is the Z per unit new. Now we know that Z per unit new equal to Z per unit old into KVB old by KVB new whole square multiplied with MVAB new by MVAB old. Okay, clear? Now using this formula we can calculate the Z per unit new for all the elements. Now first generator. Have a look, sir. Z per unit new of a generator we need to calculate. Okay, what is the Z per unit old of a generator? 0.1. What is the KVB old? 11. KVB new also 11. What is MVAB old? 100. MVAB new for complete system is what? 100. That means KVB old, KVB new same. MVAB old, MVAB new same. Z per unit old equal to Z per unit new. Clear? And because the generator rating only we are considering as base now. So that's why generator per unit impedance will not change. So Z per unit new for our generator is 0.1 per unit. It will remain same. Next, coming to transformer 1. For transformer 1, what is the Z per unit new? Z per unit new of a transformer equal to Z per unit old, which is 0.2 multiplied with, very simple, KVB old by KVB new whole square. So you can calculate either from primary side or secondary side, you will get the same answer. Okay, so from the primary side I am doing, let's see what is the KVB old, its rating, how much? 10. KVB old is 10, right? What is the KVB new we are calculated? Generator rating, sir, 11. Up to here what? KVB new is what? 11. So 11 is the KVB new. 10 by 11 square into what is the MVAB old? 150. MVAB new is what? 100. So MVAB new by MVAB old. So 100 by 150. If I solve this, we get 0.55 per unit approximately. That's what the transformer 1 new per unit impedance. Now coming to transmission line. But transmission line, you just notice here, actual impedance is given. So I can directly calculate the per unit impedance by dividing with what? Base impedance. Okay. But we need to calculate the base impedance of transmission line. But base impedance of new value we need to calculate. Okay. What is the KVB new in the transmission line circuit? 110 kV. KVB new in the transmission line circuit is 110 kV. What is the MVAB new in the transmission line circuit? 100 MVA. For complete system, MVAB new is what? 100. So that's why. So for a transmission line, what is the Z base new? KVB new is 110, MVAB new is 100. So 110 square by 100. So 110 square by 100 is 121 ohms. Clear? That's about Z base new. But what about the Z actual of a transmission line? 50. So that's why directly I am writing Z per unit new of a transmission line equal to Z actual is 50. 50 divided with what? 121. So I will get 0.413 per unit. That is for transmission line. Now after the transmission line, who is the next element? Transformer 2. Okay, for transformer 2 now. So what is the Z per unit new for a transformer 2? Z per unit new equal to Z per unit old, that is 0.2. Okay, multiplied with KVB old. Either you look from HV side or LV side. Okay, I will look from HV side now. What is the KVB old? The rating, HV side rating 120. 120. KVB old is 120. KVB new, HV side KVB new till here 110. So 120 by 110 whole square multiplied with MVAB new by MVAB old. MVAB old is 75, MVAB new is 100. So 100 by 75. If I solve this, we get 0.384 per unit. That's about for transformer 2. So finally we left with motor only. Okay, after transformer 2 we will calculate for motor. Now let's see, sir, I am doing here for a motor. For a motor, what is the Z per unit new? Z per unit new of a motor equal to Z per unit old is 0.1, okay, 0.1 multiplied with what is the KVB old? KVB old is motor rating 20, but what is the KVB new? Sir, if you convert the KVB new on the motor circuit, what I got? 110 by 6. So I can write here 110 by 6 whole square multiply with MVAB new by MVAB old. MVAB new is 100, MVAB old is what? 50. So if I solve this, we get 0.283 per unit. So the per unit impedance of motor is 0.283 per unit. So finally we calculated per unit impedance of a generator, new per unit impedance of a transformer, new per unit impedance of a transmission line, and transformer 2, and also for motor. Now coming to the next example. So in this example is asking to draw the impedance diagram by considering transformer rating as base. Transformer rating as a base we need to calculate. Anyway, and also we need to calculate what is the driving point impedance of bus 1, bus 2 and bus 3. Okay, clear? But before doing for calculation, first we have to convert all the per unit impedances onto what? Common base. Okay, that means the per unit impedance of every element onto common base. Clear? But clearly mentioned transformer rating as base. Transformer rating means primary side voltage rating is 10 kV, secondary side voltage rating is what? 100 kV. So that's enough, only one transformer is there. So what is the high voltage side rating? 100 kV. That means what is the KVB new on this side? 100. What is the KVB new on this side? Transformer rating as base clearly mentioned. KVB new here is what? 10. So low voltage side KVB new is 10, high voltage side KVB new is 100. Clear? But what about the MVAB new for complete system? MVAB new I am asking. MVAB new for complete system is transformer rating as base. That means what? 50. Clear? Now we need to calculate for all the elements what is the new per unit impedances. First we start with generator. Generator, what is the KVB new? 10. What is the KVB old? 11. What is the MVAB new? 50. What is the MVAB old? 100. What is the Z per unit old? 0.1. So directly I am writing, don't confuse sir. Generator Z per unit new by default. This is the new value only. Okay. I am not writing Z per unit new again. This is a new impedance. Okay. 0.1. Clear? Is the Z per unit old. Then KVB old by KVB new. KVB old is the rating of the generator 11 and KVB new is what? 10. 11 by 10 whole square. Then what is the MVAB new? 50. MVAB old is 100. So 50 by 100. If I solve this, we get 0.242 per unit. 0.242 per unit is the generator new per unit impedance. Transformer The new per unit impedance is same as old per unit impedance. Why is clearly mentioned. Consider the transformer rating as what? Base. Consider the transformer rating as base. That's why what is the Z per unit for transformer? Same, 0.2 per unit. Clear? Now after that, transmission line. So transmission line actual impedance is given. Check, 50 ohms is given. You need to calculate per unit impedance by dividing with what? New Z base. What is the new Z base? What is the new KVB? New MVAB you need to check here. What is the new KVB? 100. What is the new MVAB? 50. So what is the Z base? ZTL is given 50. What is the Z base here? KVB new square by MVAB new. KVB new is what? 100. MVAB new is what? 50. That means 100 square by 50. So we get here 200 ohms. So that means what is the Z per unit for transmission line? 50 by 200, which is 0.25 per unit. 0.25 per unit. 50 by 200 is 0.25 per unit. Okay. Now we can draw the impedance diagram. So how to draw the impedance diagram? Very simple. Generator means a voltage source in series with impedance. This is bus 1. Okay. So voltage source means EG. Fine. What is the generator impedance we got? New impedance 0.242 per unit. I will write here 0.242. Then after that, between 1 and 2 buses we have a simple transformer. Clear? Transformer is simply represented in what? Series impedance in per unit form. What is the transformer impedance? Old is 0.2, new also 0.2. So new you have to take 0.2 per unit. But transmission line, what is the new per unit impedance? 0.25 per unit. Fine. So that's it. That's it. That's about the impedance diagram. Now this is bus 1, bus 2 and bus 3. What is asking? Driving point impedance, nothing but Thevenin's impedance. So if you look the Thevenin's impedance at bus 1, sir, you just hold like this. If I hold like this side is open circuit. Okay, so these two impedances will not coming into picture. If I look from impedance, if I look from here, the closed path is exist from here only, not from here. Suppose if there is a closed path here, for example, then this and this will be in parallel. But this is an open circuit, but because the transmission line is just floating, not connected to any element after that. So that's why the point is clear. If I look from bus 1, that's it. There is no closed path here, there is a closed path here. But when you are calculating driving point impedance or Thevenin's impedance, both are same, you need to represent the voltage source as what? Short circuit. Now if I look here, from here to here, how much impedance? Only 0.242, because this is not coming into picture. That's why I can directly write Z Thevenin at what? Bus 1. Or driving point impedance of bus 1 is what now? 0.242 per unit. Okay? The Thevenin's impedance or driving point impedance are same. That is what now? 0.242 per unit from here. Okay, that's about the bus 1. Now I am writing for bus 2. Have a look. Bus 2 means what? You have to look from this terminal. Indirectly, this is not coming into picture, but these two coming in what? Series. Have a look. These two are coming in series. If I hold like this, these two are coming in series. So 0.242 and 0.2 will be what? 0.442 per unit. Z Thevenin 2 is what? 0.442 per unit. Now finally, Z Thevenin 3, that means the driving point impedance of bus 3. If I look from these two terminals, all these three will coming in series. Here I am observing now at bus 3. So Z Thevenin at bus 3 is what? 0.25 plus 0.2 plus 0.242. So what I get now? 0.692 per unit. 0.692 per unit. That's about the driving point impedance of bus 1, bus 2 and bus 3. Now we will see the basic formulas in actual form and in per unit form, so that we will not get any confusion when we come across problem solving. So this table is very, very important. So clearly observe. So first we will proceed with star connection, sir. For a star connection, what is actual line voltage and phase voltage relation? Actual line voltage equal to √3 times the actual phase voltage at an angle plus 30 degrees. And the phase voltage actual equal to line voltage by root 3 at an angle minus 30 degrees. Clear? And the line current equal to phase current. So this is in actual form. Now we will see in per unit form. Sir, in case of per unit form, the actual line voltage is equal to, I am not writing VL per unit, by default this column for per unit. Actual line voltage in per unit form equal to phase voltage in per unit form at an angle plus 30 degrees. And phase voltage in per unit form equal to line voltage in per unit form at an angle minus 30 degrees. Okay? Line current in per unit equal to phase current in per unit. That's about for star connection. Now we will see delta connection, sir. For a delta connection, the line voltage equal to phase voltage, line current equal to root 3 times the phase current at an angle minus 30 degrees. Otherwise, the phase current equal to line current by root 3 at an angle plus 30 degrees. Whereas in per unit form, line voltage in per unit equal to phase voltage in per unit. That is true. Line current in per unit equal to phase current in per unit, but at an angle minus 30 degrees. And phase current in per unit equal to line current in per unit, but at an angle plus 30 degrees. Now we will see complex power S. Now the complex power S can be written as 3 into V phase into I phase conjugate. This is a complex power. In this, real part is what? Active power. Imaginary part is what? Reactive power. We already discussed in PS1. Once again I am writing here. Okay. Now, shall I write like this? Root 3 VL IL conjugate. Is this valid? No, this is blunder. Why? Because, sir, if I write V phase I phase conjugate, then the complex power, we get a magnitude and phase angle. Phase angle represents the angle between phase voltage and phase current. That is correct. Because the phase angle of the complex power should be power factor angle. We discussed this point clearly. So, to get a power factor angle, we know that the power factor angle is always angle between phase voltage and phase current, but not line voltage and line current. But if you use this formula, we get a magnitude and phase angle. But that phase angle represents the angle between line voltage and line current, which is not a power factor angle. That is why this formula is not valid. Only 3 into V phase I phase conjugate, that is equal to P plus JQ. This formula only valid. So that is in what? Actual form. Now in per unit form, this S actual must be divided with S base. Okay. So tell me what is S base formula? S base equal to, we know that 3 times V phase base into what? I phase base. They are just having magnitude, no phase angles here. 3 times V phase base by what? I phase base. Clear? So if I divide S actual with S base, 3 get cancelled. The 3 multiplications will not come. So what is the complex power in per unit? So 3 get cancelled. So V phase per unit multiply with what? I phase per unit conjugate. In this, real part is what? P per unit, and imaginary part is what? Q per unit. Clear? So the real part is the active power per unit, imaginary part is reactive power per unit. Simply V phase I phase conjugate, nothing else. Again I am saying, sir, why we written the formula like this? Careful, since this 3 get cancelled, but generally many people what they will do is, they will again say 3 into V phase I phase conjugate in per unit. No, that is blunder. When you are dealing with the per unit quantities, again I am saying, the 3 multiplications and 3 divisions, root 3 multiplications and root 3 divisions will not at all come. The blind way to remember, sir. Root 3 multiplications or divisions will not come in per unit system. Okay. Now that's about the complex power formula. Now we will see active power and reactive power. So what is the formula for active power? Active power, we know that P, that is equal to 3 magnitude of V phase, magnitude of I phase into cos phi or cos theta, better to say cos phi, where phi is the power factor angle. Okay, clear? This is in actual form. Now you divide this with S base. What I get S base is what? If I divide this with S base, we get P per unit. 3 get cancelled. V phase by V phase base. V phase per unit. I phase by I phase base. I phase per unit, and cos phi is as it is. So that means what we get here is P equal to V phase into what? I phase into what? Cos phi. These values are in what? Per unit. Careful, sir. In per unit, voltage per unit, current per unit, multiply with what? Cos phi. Okay, clear? So that's about P. Clear, sir? And you will also write like this. So before that, S base can also written as root 3 into what? V line base into what? I line base. This is valid because you are just multiplying the magnitudes. Okay, S base equal to root 3 into V line base, I line base also valid. Anyway, P also can be written as what? Root 3 V line into what? I line into what? Cos phi. This is also valid. So here also, so if you divide with what? Root 3 V line base and I line base, V line by V line, V line per unit, I line by I line base, I line per unit. So that means what I can write now? VLIL cos phi. Now generally people have confusion. Is these two formulas are same? 100% they are same. Why? Because irrespective of the connection what you are dealing, magnitude of the phase voltage, magnitude of the line voltage in per unit form are same. Magnitude of the phase current, magnitude of the line current in per unit form are same. That's why don't confuse, sir. Clear? Now what about reactive power, sir? Reactive power formulas. So Q equal to what? 3 into V phase I phase sin phi. Okay, but what about here? We can also write root 3 V line I line sin phi. Now we are just dividing with what? The base values. So that's why what I get here, P equal to simply V phase I phase sin phi. Otherwise V line I line sin phi. Now careful about these formulas, which are very important. Again I am saying in per unit form, the 3 multiplications or division with 3 or multiplied with root 3 or division with root 3 will not come. So with this I am concluding this lecture. So in the next lecture we will see some numerical questions, and then we will go for the next chapter, which is symmetrical components and sequence networks.